Electrical energy. Okay, it's going to be notes number 6. So go ahead and open to notes number 6 if you're not already there. Electrical energy. All right, we're going to start. Stop. Understand? We're going to start by reviewing the definition of energy in general. So this is the exact same slide that we had on the light energy notes yesterday. This is the part I want you to copy down. Energy is the ability to do work. That's what goes in the first part. What is energy? Energy is the ability to do work. Now, I said this slide is exactly like the one from yesterday, and I was wrong. It's not exactly like it, but this part's the same. Down here, we talked about the different forms of energy, okay? But the ordering on them is a little different. Okay, so you kind of ignore this part down here. But the 5 different kinds of energy. We have light energy, which we discussed yesterday. Mechanical energy, sound energy, thermal energy, and electrical. We did light yesterday. Today we're going to do electrical energy. Next week, we're going to briefly look at these 3 altogether. That will be notes number 7. Okay? So today we're going to focus on electrical. All right? So, what is electrical energy? It is a form of energy produced when electrons move from one place to another. Yes. Not right now. Later we can. Electrical energy is a form of energy produced when electrons move from one place to another. Okay? So, hopefully you know the answer to this, but what is an electron? An electron is the subatomic particle, meaning the small part that builds up an atom, okay? It's one of them. There are 3. The others are protons and neutrons, but they're in the nucleus, okay? The electron is the particle that's actually spinning around the nucleus of the atom all the time, okay? There are usually, depending on the atom, there could be 1 electron, there could be 35 electrons, could be 49 electrons, whatever it is, okay? But the electrons are constantly moving. I can't show you that in a picture because pictures don't move. But in reality, the electrons are spinning around the atom at a very, very, very high speed, okay? All the time. Now, that movement is not what creates electricity. This happens all the time. This is happening with the mouse. This is happening with the board. This happens with the marker. These are not electrical, right? I can hold this all day long. It does not have electricity, okay? The atoms in it are still moving, but this movement is not what creates electricity. What creates the electricity is when the electrons jump from one atom to another, which I'll get to in a minute, okay? Electrons are constantly moving. The movement of these electrons depends on how much energy the atom has. Landon, you okay? Okay. This means that every object has potential energy because every object has atoms that have electrons spinning around. Although some have more than others. The electrons are constantly moving. This movement depends on how much energy it has, which means that every object has potential energy, but some have more than others. Nicholas. The shells, yes. Yeah, and they lock ways. Correct. Mm-hmm. That would produce light energy, though. That's when electrons glow. Yeah, that's correct. Okay, so to generate electrical energy, we can do that when we succeed in causing these electrons to move from one atom to the other with the use of magnetic forces. Davin, don't worry about that right now. Worry about the notes. Okay? So, as I said, here's the atom. Protons and neutrons are in the middle. Electrons are spinning around the outside. Okay? Now, what you have to understand is what keeps these electrons spinning around the atom and not just flying off into space. That is caused by this force of attraction between the protons and neutrons and the electrons. Okay? Just like magnets have this force that pulls them together, right? The electron is held in orbit, so to speak, around the nucleus by a magnetic force. Okay? They're drawn to each other. Okay? When we can succeed in having a more powerful force, pull that atom out of orbit and jump to a different one, that jumping is what creates electricity. Okay? So it's kind of like this. What happens if I walk around shuffling my feet on the carpet all the time, and then I go to touch Parker? What happens? Bella, what happens? I'm going to shock him, right? Okay, here's what happens. This is the explanation for that. As I'm shuffling my feet around on the carpet, I'm picking up more and more and more electrons on my body. So I am becoming electrically charged. Okay? When I go to touch Parker, who has less electrons on him at the moment, when I go to touch him, the shock is my body transferring my extra electrons to him. Okay? Have you ever been shocked before you can actually see the electric spark?
Yeah.
Okay?
I do that under my blanket.
Stop doing it. Put your shoes back on. That is actually lightning on a very small scale. Turn around here. Okay? So, that jumping of electrons is what causes the spark. Now, when we can cause electrons to jump around all the time, we can get a constant flow of electricity. Okay? Lightning is one good example of electricity in nature. So powerful that it is not confined to a wire. Okay? We cannot trap electricity on a wire. If electricity hits a wire, it causes the circuit to blow. Right? That's when our power goes out and we have lots of problems. Okay? Lightning is a very powerful form of electricity. What happens with lightning is the thunder clouds in the sky. When you hear thunder, that's actually the clouds and the air masses bumping against each other. Okay? When that happens, it's like when you take two balloons and rub them together. That creates static, correct? Okay? When the thunder clouds are bumping against each other the whole time during the storm, it's building static electricity. Eventually, those thunder clouds get so electrically charged that the next time they bump, the electrons jump from one atom to the other, causing the big shock, which is what we see as the lightning. Okay? So, next time you're in a thunderstorm, you can impress all your friends and your parents and your brother and sister and cousin and dog by saying, oh, those electrons are very busy up there. They're going to be like, what? Then you can explain what lightning is. The electrons jumping from one cloud to the other. Okay? So, in your notes where it says, what is one example of electrical energy in nature? You write lightning. Okay? Last part, and then we're going to pause for questions for a second. Electrical energy is usually transferred through wires. Electrical energy is usually transferred through wires. Now, what makes the wires work is the material on the inside of them must be a good conductor. Oh, conductor. This is not in your notes. Don't freak out. Okay? If the material is made of an insulator, also not in your notes, don't freak out, okay, the electricity will not flow. If I have electrical wiring made out of paper, that's not going to do me any good. Paper is an insulator, not a conductor, okay? But it is important that I have a conductor on the inside and an insulator on the outside. Why? Because if I go to grab an electrical wire, like if I had a plug here, if I touch the wire, If it's not covered in an insulator, it will shock me. Okay? Have you ever seen electrical wire that's kind of broken or it has like part of the plastic is ripping off? You don't ever want to touch that. Okay? Because if electricity is flowing and you touch the conductor, it will conduct to you and shock you. Okay? That's why you only want to touch the plastic part or the insulator. Okay? All right, I'll take. Oh, we gotta hurry. I'll take 3 questions. Okay? Let's do Sophie, Parker, and Connor. Sophie.
You know how you said it like softly?
Uh-huh.
Well, like when you use a charger with like the thing that plugs in the outlet, is that softly?
If you're touching the conductor, like the metal part of it, it could.
Oh my god, I licked it.
Was it in the wall? When you licked it?
the battery.
Oh, okay, no, not smart.
Yeah.
Very
And
nice.
then since it shocked me, it kept licking it.
What the heck?
You licked the battery.
Parker?
Excuse
Excuse me.
I didn't get on my notes I didn't get so this means every object has potential energy, even though some have
More.
and then also the electrons can move from one atom to another with the use of
Magnetic. Connor?
I didn't get what is it one example of electricity energy in nature.
Lightning. Are you missing part of your notes? Okay, so I'm gonna move on. It's just your notes fell apart. Okay, do the notes for today. During time break, I'll help you put them back together in order. Okay, what is an electric current? This is the next part. An electric current is the constant flow of electrons through a conductor. Okay? Now, depending on how strong or weak the current is, will determine how bright the light bulb will light up, or the component. Okay? Usually we use a light bulb as the component, but we'll get to that more later on. Now, if the flow of current through this path is strong, there's a lot of electrons flowing through, the bulb will be very bright. If there's not a whole lot of electrons flowing through and the current is weaker, the bulb will light but very dim. Okay? Current is the amount of flow going through the circuit. What is a circuit? An electric current has to have a path through which it can pass. Another name for this path is an electric circuit. This is the next part of your notes. An electric current must have a path through which it can pass. Another name for this is an electric circuit. Okay? Now, there's 2 ways we can define an electric circuit. One's a little longer and more complicated. One's a little easier. Here's the longer, more complicated definition. An electric circuit is a complete path of conductors that electrons flow through, moving energy from component to component. Okay? The easier definition, it's a path or a big loop in which an electric current flows. Alright? So this circuit has a little bit of a box shape with a little rectangle here on the outside. Okay? The circuit could take any kind of shape. Okay? But the path the electrons flow through is on the conductor. Again, if your connectors or if the wirings are made of an insulator, the circuit will not work. Okay? It's got to be a complete path of conductors that will transfer the electricity. Okay? Alright. Last part on this page. On the front page, right? Yes. An electric current will not be able to flow through a circuit with a break in it. Okay? This is called an open circuit. Raise your hand if you've heard of open and closed circuits before. Good. This should hopefully be a review. An open circuit, a circuit that is not connected in some area so that electrons do not flow through. In this kind of a circuit, electricity is off. Okay? So, talking about the circuit. I told you the electrons will only flow if all these conductors are connected. Okay? But if they're not, here's what happens. The battery tries to send electrons. Okay? But the electrons travel through the path. They get here and realize, wait a second, we can't go anywhere. So they go back and they don't flow at all. Okay? If I were to touch these two wires together and close the circuit, then this would light up. The circuit would be on. Okay? Another example of an open circuit is not necessarily one that has a break in the wires, but one that has a switch that is open. Okay? In this case, this would be like a metal rod. Okay? If I touch this metal rod to this metal part, that will close the circuit, like closing a gate. Okay? Then the electricity will flow and the light bulb turns on. But if I turn the switch off or I disconnect the switch, now it's an open circuit, and what happens to the light bulb? It goes off. Okay? In order for it to turn on, the circuit has to be closed all the way through. Yes.
I have these things called snap circuits.
Yeah.
Yes.
I have those too back there.
Yeah, if you make like a circuit, you have to connect one side to the like battery. And then make it go around, and then like do like a light or like a fan or something. And then but you have to connect the other side to the other side of the battery.
Very good. Yeah. Now, what Parker is saying is true. Batteries have a positive and a negative side. In order for the electricity to flow, one side has to be connected to the positive, one's got to be on the negative. If both wires connect to the same side of the battery, it doesn't work. Okay? Same thing here. The two knobs on top, some batteries will look like this. One's a positive knob, one's a negative knob. If you connect both wires to the same knob, you have a problem. It won't work. You have to have it connected to the positive and the negative. Okay? Yes.
Two things. One, will an electrical wire, will it stop working if the wire's too long for the electrical current to go through? And once my grandfather, he was trying to work on electricity, and he got shocked by it, and it blew off his pinky, like his pinky toe.
Oh,
I
it blew
know.
it off?
It blew it off.
How far did it go?
I don't know.
That's crazy.
That's what my mom told me. So he only has 4 toes.
Alright, so this is our diagram of an open circuit. Okay? You can see obviously the wire is broken here. In order for this to be a closed circuit or to turn the light bulb on, you would need to connect this wire down here to the other part of the component. Okay? Now, a circuit that is complete, one that actually works, is a complete circuit that allows electrons to flow through completely. That's what we call a closed circuit. It's complete. There is no break in it. In this kind of a circuit, electricity is on. Okay? So, you can see here it's a complete path. So, the electrons are flowing, running around all the way through all the time. Therefore, the light bulb turns on. Okay? In this one, over here, it's also connected, right? The wire goes to the positive side, wire goes to the negative side. This light bulb would be turned on. Now, what if, Connor, I have this circuit, okay? What if there's a break right here? Connor, what happens to the light bulb?
The light bulb turns off and
Correct.
it cannot come on until they go back together.
Correct. Exactly. That would be called a what kind of circuit?
It would be called an open circuit.
An open circuit. Very good. Okay? So, in an open circuit, this one, okay, the light bulb would be turned on. Make sense? Sorry, closed circuit. Thank you. Closed circuit, light bulbs turned on. Now, this is going to be, I think, our last part. There are 4 parts of a circuit. Okay? 4 parts. Number 1, you have the power source. This is like the engine. Okay? What creates the power or what is generating it. Okay? Usually it's a battery. or some kind of generator. Once you have the power source, there's usually some kind of component. All right? The component is the part you're trying to turn on. Most commonly, it's a light bulb. Could be a buzzer, it could be a fan, it could be a beeper, it could be all kinds of things. Okay? But it's the electrical item you want to turn on with the circuit. Third part of your circuit is connectors. These are most always some kind of wire. Okay? And then sometimes, not all the time, this is the one thing that you could maybe have, maybe not, but this would be a control device, usually a switch. Okay? Now, that could be a switch that you flip on and off, like a light switch. Could be a switch that you open and disconnect, or close to connect. See what I'm saying? Okay. Yes.
It seems like any word that has to do with electricity, like for example motor, if it sounds like it would, the end would be ER, it's actually OR.
Yep.
I don't know like why that happens.
Motor.
Yeah.
Kayla?
I'm missing the top note on the electronic key. I can help you.
Thank you. That would be great. Almost. All right. Last part for today, the switch. Okay? The switch opens and closes the circuit by bringing together or separating two pieces of metal. When the metal pieces touch, the circuit closes. When the metal pieces separate, the circuit opens. Okay? So, kind of the old school way is this lever right here. Okay? Notice the part that you grab is covered in rubber, an insulator. Okay? So that when you close the switch and cause these two pieces to touch, you're not going to get shocked by the electricity. Okay? Here, the switch is the same way. Because the switch is up and these two parts are not connected, it's open. But the minute you push this down and close it, the circuit would be on. Light bulb turns on.
Close.
Yes, thank you. We have the closed circuit. Make sense? Okay. Now, let me explain the homework to you real quick. Don't put these away because you're going to want the notes to do them. Let me stop this first. I think they're